Hello and welcome. In this lecture we will be looking at PI control of the surge tank, temperature control of the surge tank using a PI controller, where the integral time has been taken to be less than the tank residence time tau, and we'll derive analytical expressions for the solution of the governing ordinary differential equations. That's the agenda for this lecture. So let's get going. So the base case conditions of the surge tank, and we are trying to do temperature control, trying to maintain temperature at the set point, and the temperature controller is a PI controller. This is the process dynamic model, and then you have the controller equation. The residence time at the base case conditions is 10 minutes, and the temperature to Q heating duty gain is 0.4, where Q is taken as a percentage of the base case value. So now if you look at the governing equation, the governing equation is, and I'm dropping the tilde relationship. The deviation variable tilde is dropped. If I say t, it's understood it is t deviation from steady state value. So if t is the deviation from steady state value and t naught is the deviation from the steady state value, this is what we have. And if I put for Q% the PI controller, then what we get is K times Q% is Kc times T set point minus T. By the way, T set point is actually not T set point but deviation from initial value, and T is also deviation from initial value. And because we are working with deviation variables, there will be no bias term. So there will be no bias term. Now to eliminate the integral, differentiate both sides of the above equation. So what you get is into tau I plus temperature set point deviation variable minus this is what we get. And if I take the temperature terms to the left hand side, then what we get is and maybe I'll also take tau and multiply by tau I by kkc, then what we get is this. Tau I by kkc into, I think it will be 1, tau I by kkc into 1. So it will be, I think, 1 plus kkc. Just see if this is correct. Uh, 1 tau I by kkc. Tau I by kkc plus tau I. So tau I common. Tau I plus tau I by kkc. So if I take tau I by kkc common, then 1. And kkc, yeah, so that should be fine. Yeah, so this is fine. Plus t is equal to so this is the servo part, and this is the regulator part, disturbance. And if you look at the characteristic equation of, now we are saying that tau I is less than tau, and so let's just say tau I is equal to tau by r, where r is greater than 1, then what we get is tau square by r kkc, second derivative of temperature, plus times first derivative of temperature, plus T is equal to plus tau by r dt set point by dt plus t set point. So this is my governing differential equation, and this governing differential equation must be solved for the servo response and for the regulator response. We'll look at the regulator response first. So if you look at the regulator response first, then TSP, deviation in temperature set point, is 0. So for the regulator response, this term goes to 0. Whether you are looking at the regulator response or the servo response, the homogeneous part of the equation remains the same. So the characteristic equation that governs the homogeneous response, that determines the fundamental exponentials, the eigenfunctions that satisfy the ordinary differential equation, the homogeneous part of the ordinary differential equation, will come from the characteristic equation after some algebra will turn out to be lambda square plus rkk 1 by tau into 1 plus kkc times lambda plus r times kkc by tau square. This is the characteristic equation, and for this characteristic equation the two roots of the characteristic equation are lambda is equal to minus 1 plus kkc divided by 2 tau plus minus square root 1 plus kkc whole square, and tau square square root of that will be tau, so we'll take the tau out, minus 4 times r kkc divided by tau square, and tau square will take and divided by 2, so this would be divided by 2 tau. So these are the two roots, and we'll take the case, there are several possible scenarios, so we'll take the case where the determinant is less than 0, so you get imaginary roots. So what is the condition for, you can see from the roots, if kkc is very small, then this term goes to 0, the negative term goes to 0, this is positive, and so you got two real distinct roots. As kkc starts to increase, the square term increases faster than the linear kkc term, so so if kkc is small, then what will happen is square of a small number is a very small number. So if kkc is small, you will get the linear term grows faster than the square term, so you will have imaginary roots because the thing under the square root sign would be negative. But if kkc is increased sufficiently, then the square of term will start to dominate, and then you'll again get positive part under the radical, and then you'll get real distinct roots. So for kkc tending to 0, you get real distinct roots, and then there is a minimum value of kkc and a maximum value of kkc between which you get imaginary roots. So what are those values? Those limiting values correspond to the determinant disappearing. So when the discriminant disappearing. So what is the discriminant? The discriminant is 1 plus kkc whole square minus 4r kkc, and this discriminant becomes 0 at kkc whole square plus 2 times 1 minus 2r times kkc plus 1 equal to 0, and this discriminant will become 0 when the discriminant of this equation becomes 0 when, or the roots of this equation, not discriminant, the roots of this equation are k, so the discriminant of the characteristic equation goes to 0 when kkc satisfies this equation, and the roots of kkc are minus 1 minus 2r divided by 2 plus minus square root 4 into 1 minus 2r whole square minus 4 divided by 2, and There is a 2 here, sorry. So this 2 and this 2 and this 2 and these 4s cancel out, and so what you get is kkc, by the way there is a minus sign here, so is equal to 2r minus 1 plus minus, so this is 2r minus 1 plus minus 2 times square root r times r minus 1, if I'm not wrong. Let's see, so a square minus b square is a minus b into a plus b, so 2r minus 1 multiplied by 2r minus 1 plus 1. So this would be 2r and this would be 2 times r minus 1. So 2 comes out of this radical. Yeah, so this is fine. So these are the two limiting values of kkc, and so if kkc is between these two limiting values, then we will get imaginary roots, conjugate complex roots for the characteristic equation. And so the condition for kkc is kkc should be less than kkc max and should be greater than kkc min, and kkc max is going to be what? The one with the plus sign is going to be 2r minus 1 plus 2 times square root r times r minus 1, and kkc min is going to be 2r minus 1 minus 2 times square root r times r minus 1. So if kkc is between these two limiting values, then you get complex conjugate roots. This will give complex conjugate roots. And what are those roots? Well, those roots are going to be, the complex conjugate roots are going to be what are the complex conjugate roots going to be? The complex conjugate roots are going to be, you will have lambda is equal to minus 1 plus kkc divided by 2 tau plus minus j times square root 4r kkc minus 1 plus kkc whole square divided by 2 tau, and let me call this a and let me call this b, and so what you have is lambda, there are two roots, so 2 lambda is equal to minus a plus minus jb. These are the two roots of the characteristic equation. If these are the two roots of the characteristic equation, then if I am forcing, if the right hand side of my governing ordinary differential equation is actually a step and not derivative of steps as in the equation here, not the derivative but only a step, if the forcing function was a step, then the total solution T is going to be 1 plus, where 1 is the particular solution and step is a unit step. So T is going to be, for a step, is going to be 1 plus lambda 1, sorry, 1 plus C1 times e to the power minus a plus jb times t plus C2 times e to the power minus a minus jb times t. Okay, so this is going to be the solution. This is just method of constant coefficients. And now we will obtain C1 and C2 from the initial conditions. What are the initial conditions? The initial conditions are very straightforward. T equal to 0 at time t equal to 0 and dt by dt is equal to 0 at time t equal to 0. So if we just apply this very simple initial condition, two initial conditions, we should be able to get C1 and C2. So from the, so initial conditions are, from initial condition t equal to 0, at t equal to 0, temperature equal to 0 gives C1 plus C2 is equal to minus 1. And the second initial condition, or the derivative disappearing at time t equal to 0, time derivative of t, of temperature disappearing at time t equal to 0, it will give us minus a plus jb times C1 plus minus a minus jb times C2 must be equal to 0. And now what we will do is, if you multiply the top equation by minus a plus jb and subtract the 2, then what you will get is minus a plus jb and subtract, so plus a plus jb times C2 should be equal to minus 1. Is that right? Hang on. Yeah, so this cancels out, so plus a minus a plus jb plus a plus jb equal to minus 1. Yeah, okay, so minus a and plus a cancel out, and so what you get is C2, this initial conditions imply that C2 is equal to minus 1 times minus a plus jb. So C2 will be a minus jb, is that right? C2 will be a minus jb divided by twice of jb, and C1 will be, replace minus j with plus j, that's what C1 would be, minus j, so a plus jb, okay, a plus jb, so it will be a plus jb minus divided by 2 times jb. Okay, so this is what C1 and C2 turn out to be. And so if we substitute this into the expression for temperature, the analytical expression for temperature is then obtained, and so let's just do that. So if you do that, what you will get is t is equal to 1 minus a plus jb divided by 2jb into e to the power minus at times e to the power jbt plus a minus jb divided by 2jb e to the power minus at into e to the power minus jbt. This is what we get. And now you say, okay, let's take the b out. Let's take e to the power minus at out, negative of that, so we'll get 1 minus e to the power minus at is common. B is also common, so we'll take these things out. And so what you get is a plus jb into e to the power jbt. And so if I take my yeah, so minus, so you're going to get plus by minus minus plus, so it will be, yeah, minus minus minus, okay, fine. So it will be a minus jb, because you're multiplying, so so yeah, this is fine. Hang on. And so this guy times e to the power minus jbt divided by 2j. And so this complex number a plus jb, a is a positive number, b is a positive number, so the complex number a plus jb is like this on the complex plane. This is real part, that's imaginary part. So you got, this is a and this is b, so this is your complex number a plus jb. In polar form, this would be, its magnitude will be square root a square plus b square times e to the power j phi, where phi is this angle, this angle phi is equal to tan inverse imaginary part by real part, which is b by a. So the complex number a plus jb can also be written as this, and a minus jb can be written as square root a square plus b square into e to the power minus j phi is what it will be, because b has become minus b, so magnitude remains the same. Now your complex number is this guy, angle has become, instead of phi, minus phi. Yeah, so therefore replacing these numbers over there, what you will get is t in response to a unit step, if the forcing function is a unit step, will respond as e to the power minus at divided by b divided by square root a square plus b square. So this a square plus b square is actually in the numerator. And then what you get is, this would be e to the power j times bt plus phi minus e to the power minus j into bt plus phi and divided by 2j. And therefore what you get then is this is actually the sign from Euler identity, this is actually sine of bt plus phi, sine of the angle bt plus phi. So if a second order system with complex conjugate roots for the characteristic equation is forced by a unit step, then the dynamic response is given by, let's quickly take a look at that. The dynamic response is given by t is equal to, for a unit step, is equal to e to the power minus 80 divided by b by square root b square plus a square times sine bt plus phi, where phi is equal to tan inverse b by a. So this is the response. You can see that this is a sinusoid multiplied by an exponential. The sine wave always oscillates between -1 and 1, but for a positive a, e to the power minus 80 will become slower and slower and slower. And so if you have a second order system forced by a unit step, the response would look something like this, where this is the exponential and the sine wave is oscillating like that, and this is the e to the power minus 80 cover, and then the sine wave when you multiply with that. So this is the kind of response that you can expect for a second order system with complex conjugate characteristic equation roots. Now for our system there are two possibilities. You could have the servo response or you could have the regulator response. Now the regulator response is obtained when change in temperature set point is 0 but T naught changes, and if the forcing function for the regulator response is you have the left hand side. The forcing function is not a step, but for the regulator response the forcing function is not a step but tau by r k k c times d by dt of T naught. So if T naught is varying as a step, then if the forcing function was a step, this would have been the response, but the forcing function is the derivative of a step times tau by r k k c. So therefore the actual response is going to be, T actual is going to be tau by r k k c times d by dt of, if this equation is a, right hand side of a. That's what it's going to be. So let's do that, and as we do that, some amount of algebra will have to be done to get the regulator response. So let's just do that algebra and get the regulator response. So let's see. Alright, so the regulator response is going to be tau by r k k c multiplied by derivative of the right hand side of it. So derivative of 1 is 0, and then what you get is minus a times e to the power minus 80. I think e to the power minus 80 will become common, and of course b by square root b square plus a square or a square plus b square is common, and so what you will get is a times sine bt plus phi. This is the term that you get when you differentiate e to the power minus 80, and then when you differentiate sine bt, you will get plus, so this will have to be minus, sine will become cos, so b times cosine bt plus phi. and multiply and divide by square root a square plus b square, and then what you get is, so t will be equal to tau by r kkc. So when you multiply and then you divide, okay, so tau by r kkc into e to the power minus at divided by b by a square plus b square, and then what you get is a by square root a square plus b square sine bt plus phi minus b upon square root a square plus b square into cosine bt plus phi. And if you look at this, you know, the same triangle, real and imaginary parts, real part a, imaginary part b, so then a by square root a square plus b square is actually cos phi. So this is actually cos phi, and this would actually be sin phi, and so you will actually get t is equal to tau by r k k c into e to the power minus at divided by b by a square plus b square times sin bt plus phi. So this will be sin bt plus phi minus phi, so that will cancel out, so it will sin bt. Now if you substitute a and b, b is actually, what the hell is b? B is actually square root. Yeah, so if we start substituting, so b is actually square root 4r kkc minus 1 plus kkc whole square divided by 2 tau, and a is equal to 1 plus kkc divided by 2 tau. So a square plus b square is going to be okay, a square plus b square will be 4r kkc by 4 tau square. 4r kkc divided by 4 tau square. Okay, so this guy goes to 4r kkc divided by 4 tau square, and b is of course what it is, and therefore this 4 and this 4 cancel out, this guy and this guy cancel out, and b is square root 4r kkc minus 1 plus kkc whole square divided by 2 tau. So the 2 tau will go to the top, and therefore what you eventually will get or should get, what you eventually should get is what you eventually should get is that t is equal to so 2 okay. Okay, so Sara, can all this cancel, tau square, okay, yeah, so tau will cancel out, and from there it will have 2 tau, so tau square cancel out, 2 will be left. So I think what you should get is t is equal to 2 divided by square root 4 r k kc minus 1 plus k kc whole square. That's the b part. to वहाँ से आ गया, and then e to the power minus 1 plus kkc divided by 2 tau times t times sine of square root 4 r k kc minus 1 plus k kc whole square divided by 2 tau times t. So this is the regulator response that we eventually are able to obtain. So this is the regulator response that we got by solving that ordinary differential equation. So let's just summarize whatever we derived. So here's the process dynamic model. Tau I is less than tau. Substitute, differentiate and rearrange. This is the governing equation that we get. Characteristic equation is this guy, and put tau I is equal to tau by r. Yeah, and so when we put tau I is equal to tau by r and r is greater than 1, we get these are the roots of the characteristic equation, and the determinant is 0 when kkc is here, and so we get complex conjugate roots when kkc is between these two limits. So these roots are of this form: lambda is equal to minus a plus minus jb, and so the homogeneous part of the solution is going to be linear combination of exponentials of these two lambdas. For a unit step forcing function, the particular solution is going to be 1, and therefore the total solution, particular solution plus homogeneous solution, is going to be this guy. Initial conditions, if you apply, you get this, and then when you solve it, this is what you get as the roots, and then when you substitute, the unit step forcing function response turns out to be as shown here. Yeah, where the phase shift phi is tan inverse imaginary part by real part. By the way, let's just look at this response, because we will see this so many times. So if a second order system is being forced by a unit step, and the roots of that second order system are complex conjugate, then the exponential is e to the power real part of the root times t, because the root is this guy, minus a is the real part, so the exponential is e to the power real part of the root of the characteristic equation times t, exponential of that, times sine of the imaginary part of the root times t plus a phase shift, and the phase shift is tan inverse of imaginary part by real part of the characteristic equation root. And this guy is actually, if you look at this guy, you've got the angle phi, this is a and this is b, and so this is a plus jb. Then Or if you look at the complex conjugate roots, the complex conjugate roots are on the complex plane, the roots are minus a plus jb and minus a minus jb. So we'll just look at minus a plus jb. So this is the definition of phi. And if you look at phi, and if you look at this guy is imagine b by square root a square plus b square. So this chap can be written as e to the power minus at divided by sine of that phi angle. Yeah. Anyway, so that's that. So the exponential is the real part. The exponential part is e to the power real part of the complex conjugate root times t, and the sinusoidal part is governed by the complex part, the imaginary part of the root. Yeah, so imaginary part is b, and the phase shift comes from the ratio of the inverse tangent of the ratio of the imaginary part and the real part. So this is the imaginary part, this is the real part, this is the imaginary part, and this is the real part. So the imaginary part determines the frequency of the sine wave. That's the point that I was trying to make. So I hope that point is made. So we got the unit step forcing function response, and then when tau I is less than tau and kkc has been chosen to lie between these, regulator response will be governed by this guy. This is the right hand side forcing function is not a step but the derivative of a step times a constant. So the solution is going to be derivative of the step response times the constant. And if you do the necessary algebra, yeah, so this is what we got. Yeah, so this is what we got. If the unit step was 1, the response would have been this, but if the step size is delta t naught, well, then the response gets multiplied by delta t naught. Okay, so this is the regulator response. And for the special case where kkc is, you know, if you look at this guy kkc, the middle value is 2r minus 1. You have 2r minus 1 and you take plus and minus. So this guy is this guy and this guy is this guy. 2r minus 1 is right in the middle. So if you take kkc is equal to 2r minus 1 and substitute over there, you can see that the regulator response will turn out to be this. You can do the necessary algebra to show that. I'm not going to show it. Hang on. Okay. All right. Now let's look at the servo response. If we want to get the servo response, then the governing equation as the ordinary differential equation, the governing ordinary differential equation remains tau square by r kkc, second derivative of temperature, plus tau by r times 1 plus kkc divided by kkc times dt by dt plus t is equal to tau I times derivative of set point, temperature set point. So tau I is tau by r times dt set point by dt plus t set point. So if you want to get this response, so we know that if for a unit step forcing, temperature varies as temperature unit step. So temperature goes as 1 minus e to the power minus 80 divided by b by square root a square plus b square times sine bt plus phi. So this is what T is. So now if the forcing is this, then the temperature response is going to be tau by R, and we'll call this A, times d by dt of right hand side of A plus right hand side of A, equation A. So this is what we're going to get. So if we put it in, what we get is then T is equal to T set point is 1 minus e to the power minus 80 divided by b by square root a square plus b square into sine. So that's the T set point part. And then we take the derivative of this times tau by R plus अरे यार, what do we do? ये क्या हुआ? सब इरेज हो गया हैं? Oh, okay. So here, okay, here we are. I lost my chain of thought. So T is equal to, this is the T set point term, this is this term, and the next term is going to be plus tau by R times e to the power minus 80 divided by b by square root a square plus b square times what? Times, take the derivative man. So derivative is going to be negative का positive हो जाएगा a times sine bt plus phi minus b times cos bt. This is what it turns out to be, and we'll have to do some algebra now. So algebra gets messy, but it's doable. So what we get is 1 minus e to the power minus 80 divided by b by square root a square plus b square. So there's a sine bt plus phi term, and that is अरे यार ये क्या हुआ क्या? Okay, so if I take tau by R common, so if I take tau by R common, and we'll make this plus, then tau by R common आ गया, so this would be a so this would be a minus r by tau times sine bt plus phi. So that's the term accounted for. Everything else has been taken as common, and it will be minus b cos bt plus phi, minus b cos bt plus phi, And standard complex algebra, this will be into 1 plus well, so let's just say e to the power minus 80 times a minus r by tau whole square plus b square square root divided by b over square root a square plus b square times tau by r times, so this we'll call this cos theta, and we'll call this sin theta. Yeah, so it'll come out to be sin bt plus phi minus theta. That's what, and where theta is equal to tan inverse of what? Tan inverse of b by a minus r tau, r by tau. So this is what we get. And now if you plug in the values of a and b, so if you plug in a equal to 1 plus kkc by 2 tau and b is equal to square root of 4r kkc minus 1 plus kkc whole square divided by 2 tau, then if you plug this in into this, hopefully what you will get then is that, and do the necessary algebra, and maybe I should do the algebra, or maybe just I should leave it for you to do. I'll leave it for you guys to do. What you eventually get is as a servo response is t is equal to 1 plus 2 times r into square root r minus 1 into kkc divided by square root 4r kkc minus 1 plus kkc whole square times e to the power minus 1 plus kkc divided by 2 tau times t sine of square root 4r kkc minus 1 plus kkc whole square under the square root divided by 2 tau times t plus phi minus theta. And you can see that if you put kkc to the middle value, if you put kkc is equal to 2r minus 1, this would solve to t being equal to, for kkc, t will be 1 minus square root r into 2r minus 1 e to the power minus r t by tau cos of square root r into r minus 1 t by tau plus phi. This is what it solves to. And so the whole point of this exercise is to show that if you do the variation of parameters or method of constant coefficients, ordinary differential equations with constant coefficients can be solved. Okay, so that's one way of solving ordinary differential equations. So just to summarize, for the servo response, the governing equation is this. Response is obtained as, yeah, and this turns out to be, boy is it something. This was the expression that I wrote, and these are the expressions for phi and theta. And for KKC, the response looks like this. So this is what we derived. Array yaar, discard. So I made a mistake, so we will have to, I made a slight mistake here. Summary होने से पहले ही हमने इसको बंद कर दिया. So let me F5 it. So if we do F5, अरे यार कैसे आता है फंक्शन शिफ्ट F5 आता है क्या? Okay, why is this guy not running? And then if I do display settings, duplicate slideshow, what happens here? Let's see. Oh boy, it's not showing, huh? अभी क्या करें? It doesn't really matter. So I think we have the video is about to end, so we will just go through the motions quickly. Yeah, so the server response is this. Okay, so so let me show you. So let me show you the response that we get. And the response has been gotten for chosen value of KKC as 2r minus 1. And you can see, what can you see? As if r is increased from 2 to 3 to 4, obviously KKC is increased. So your control is becoming more and more aggressive. So you can see regulator response for a 1 degree increase in the input temperature. If you had taken no control, the output temperature would have increased to 1 degree by 1 degree. Yeah. Here with control, your temperature goes up and then returns. And this undershoot and overshoot, this is because of the sine part of the curve. This undershoot is because of the sine wave. This undershoot is because of the sine wave. Yeah. And you can also see as you make the control more aggressive, the change in Q is more aggressive. And this is also evident for the servo response. Servo response for a delta TSP of 1 degree Celsius as Kc is increased. Yeah. And the manipulation in the Q also becomes more aggressive from this guy to this guy to this guy. Yeah, so as Kc is increased, your control gets tighter and you're getting the undershoot, very clear undershoot in the regulator response. Here also there's a slight undershoot if you see closely. Yeah, so in the regulator response and the servo response, you do get undershoots that are visible, and that's because of the sine part of the response curve. And so the key observations are, there's an oscillatory response. Response speed increases with R because when R increases, Kc increases. Aggression in Q increases with R because when R increases, Kc increases, and more Kc, more aggressive the control. No steady state offset from temperature set point. You can see that the set point returns to 0 and the set point goes to the new set point, and the temperature goes to the new set point. Yeah. Now as an exercise, what I would like you to do is consider a damped spring mass system, because you do a lot of physics. You would have done this in class 12. So derive the ordinary differential equation describing the motion of the mass attached to the spring. The damping is this damping. This is a damper. This is the damper. The force of damping is proportional to c times proportional to the velocity. So the proportionality constant, force of damping, the damping force is equal to, we'll have to see the sign, but magnitude of the damping force is c times dx by dt is proportional to the velocity. Yeah. So solve the ordinary differential equation describing the motion of the mass tied to a spring, where x is the deviation from the equilibrium position. So solve the ODE for a step change in the equilibrium position of the mass when roots of the ODE characteristic equation are complex conjugate pairs. So this would depend on what the damping constant C is. Roots of the ODE characteristic equation are real and repeated. You could also get real and repeated roots. So there will be a particular value of C for which you will get real and repeated roots. The roots of the ODE characteristic equation are real and distinct. And is it possible to have purely imaginary roots? If so, solve the corresponding ODE. Yeah, I think you'll have purely imaginary roots when C goes to 0. And then your system would be a pure sinusoid. You remember when you get, see, your transient is e to the power. So if lambda is your characteristic equation root and lambda turns out to be minus a plus minus jb, so because of the real part you get this, and because of the imaginary part you get this. That's the kind of response that you get. Now if this part goes to 0, that, and this would, I think this will happen when there is no damping. You got a ideal situation, no viscous effects, no dissipation effects. So when a goes to 0, this term goes to 1 and you get a pure sinusoid. So you'll get sinusoid, your spring mass system will keep oscillating forever. I think you would have seen all this in physics. So it would be good to use the method of constant coefficients to solve this spring mass system with which you are very familiar. And choose the damping coefficient such that you could have real repeated roots, you could have real distinct roots, or you could have complex conjugate roots, or you could have purely imaginary roots. And of course, just for the sake of theory, you could also say, what if C is negative? That means instead of dissipating, you are putting in some force into the system. You are charging the system more. For C equal to less than 0, I think what you will see is your actually oscillations blow up. You may even try and do that. Okay, so this is the exercise that I would like for you to do. With that, we are ready to summarize our lecture. So what we saw was the heated surge tank with PI temperature control is described by a second order ODE. Second order ODE characteristic equation can have complex conjugate roots, and for complex conjugate roots the tau I and Kc must satisfy certain conditions. We said that tau I is less than R or less than tau, and then Kc was supposed to be between a minimum and a maximum value, and we derived expressions for that, and these expressions are given here. For a unit step forcing, response is an exponentially decaying sinusoid. And so if you have an ordinary differential equation of this kind, its roots will be this, and for these sets of roots the response is going to be this for a unit step forcing function. For the heated surge vessel, we get an exponentially decaying sinusoidal response. There is no offset due to integral action, and that's that. With this we come to the end of this lecture. I thank you for your attention and I hope to see you next time. Thank you and goodbye. This one has been a long lecture, but so it is.